Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Conrad.
Welcome back to the Reliability Matters podcast. I'm so glad you're with me today. This is episode number 99. We are only one single episode away from our 100th episode live special broadcast. It will be broadcast live on LinkedIn and YouTube on July 26th at 10 a.m. Pacific time. We'll replay clips from several of our prior episodes and hear a few comments from some of our past guests. If you're watching this on YouTube, click on the subscribe button and click the bell icon to be notified when new episodes are released, including our 100th episode. If you want to watch our 100th episode on LinkedIn, just follow me on LinkedIn. Today, we're going to talk about cleanliness testing of post-reflowed circuit assemblies. In late 2018, IPC shocked the electronic assembly industry by introducing an amendment to Section 8 of the J Standard 001G. This amendment radically changed the way industry determines cleanliness. Now, assemblers must prove their assemblies are clean enough not to experience electrochemical migration events, which could likely lead to assembly failure. This new process of obtaining objective evidence has been met with a considerable degree of confusion. To help clear up this confusion, I invited Graham Naisbitt to be my guest. Graham is an IEC 1906 Lord Kelvin Award Winner, an IEC TC91 WG2, 3, and 10 maintenance leader of 4 standards. Graham is vice chair of the IPC 5-30 Cleaning and Coatings Subcommittee, which oversees 15 IPC standards development committees and is the recipient of 14 IPC Standards Awards. Graham is also a British Standards Institution ELP 501 member. Graham is a specialist in surface insulation resistance testing, ionic contamination control, solderability, conformal coating materials and application systems, cleaning, inspection, and test. And without any further ado, let me welcome my friend and colleague, Graham Naisbitt. Wow, if your accomplishments were any greater, we'd be already at episode number 100. But hi, Graham. Thanks for joining me today. I really appreciate you being here.
It's great to be there, to be with you. Sorry about the time differential.
Well, you had the fortune or misfortune. I had the fortune or misfortune of being on opposite sides of the Atlantic. So here we go. And I should remind our audience that we are talking to you. I'm in California. You're somewhere in England.
Yeah, I'm about an hour from Heathrow Airport.
Oh, there you go. Okay.
Which is west of London.
Yeah, I was just there actually 3 or 4 weeks ago. We were there. We were there a couple weeks before the Jubilee, playing tourists throughout London. We were going on a cruise out of Southampton, so we hung around in London for a few days, and we stayed in Westminster. And what a beautiful part of London! And I've been to London many times. Westminster is kind of like the Beverly Hills of London. It was just beautiful, and where we stayed was amazing because we were literally walking distance from Buckingham Palace and the Thames and Westminster Abbey, and it was just, and it was 75 degrees Fahrenheit, and sunny, which is unusual, particularly for April.
It can be a lot cooler. That's
yes,
for sure.
It can. Yeah, we definitely looked out. It was good tourist weather. But thanks for joining me. You and I share at least one thing in common, and we have a peculiar love of talking about contamination and dirt and residues and failure mechanisms and things like that. That's how we have earned our money over the years is dealing with dirt, right? You're an expert at detecting it and setting the standards for how much is acceptable. And I'd like to think I'm pretty good at taking it off. So between the two of us, we'll have a clean world.
Excellent.
So Graham, as I said in the intro, IPC did something it may have never done before. Maybe it has, but I'm not aware of it. And IPC, of course, is a standards organization, among other things. It's a standards organization. Through its members, which is all of us, we debate. Might be too light a word in some cases, but we argue, we debate, we arm wrestle, and we forge standards, and then send them out for ratification to vote. And like any scientific-based industry, we rely on standards. And most of the time, standards tell us exactly how to do something, or maybe not how to do something, but what's expected at the end. It must fit this specific criteria. And we had a cleanliness standard for 50 years or so that told us, using a specific type of test, exactly what was good and what was bad. Anything under a certain number was ship it, and anything over that number was don't ship it, right? Pass, fail. And there were all sorts of problems with that. You know what they are, I know what they are. The industry kind of knew, but didn't want to hear it. They just wanted to, just tell me if my part is good. But that never made it into a relevancy factor, meaning if I'm building guidance systems for a 777, do I have to be just as clean as the electronic flea collar for my dog? You know, they didn't take into account cost of failure, climactic in-use environment, all that. So all this is setting up our conversation. IPC did something quite different. You were part of that. And they said, they answered the question, how clean do my boards have to be? They basically said, you tell me, and base that answer on objective evidence. That's pretty much their answer. And then they told them how to generate that objective evidence. So in a world in a very binary world, you know, zeros and ones, tell us, we only have a zero, we only have a one. Tell me kind of the story behind the new standard, and kind of in general terms, then we'll dive down that rabbit hole. In general terms, what is that new standard? We threw away pass fail and we put something else in. Like, let's get into that.
Okay. Well, as I sent through a synopsis presentation for you, Mike, and I offer that to any viewer of this particular podcast. To go back into the equation, the very first time I attended an IPC meeting would be way back in 1988. And the people that were in the room included, apart from our dear departed Dieter Bergman, Jack Brous, then of Alpha Metals. It included Brian Ellis of Protonique. And there was an argument between the three of them as to who the hell had put this stupid number into this equation, because the 1.56 sodium chloride equivalence means that it's acceptable to leave up to that amount of salt. And I use that word carefully, but that's what we're dealing with. It's ionics. And you can leave up to 1.56 micrograms on every square centimeter of your assembly surface. Really? Given the technology that's moved at such a tremendous pace over the last 50 years and more. So an absolute value of ionic contamination does not predict electrochemical reliability. And to reinforce that point is published at Apex this year, Phil Kinner, my ex-chief chemist, when I was running Humasil Europe, Phil presented a paper that showed that flux residues, especially no-cleans, tend to break down far longer into service than people realized. And at the moment, if you're trying to qualify a solder flux, whether it's a paste, whether it's hand soldering or solder wire or anything else, the requirement is, even today, that you test using SIR for 168 hours or 1 week.
And just in case,
Now,
Graham, just in case there's someone on this webinar, on this podcast that is not aware of some of our acronyms, SIR, of course, surface insulation resistance testing, right? So we'll get into that, what that test is, but I just want some of our audience that might be visiting us from other industries to understand what SIR means.
of course,
Sorry, go ahead, Graham.
okay, I'll come on to that in a moment.
Great.
My point is only in the context of ionic contamination measurement alone, you can't use as a single quality indicator. Unfortunately, it was the US military who decided we needed to have a stake in the ground, and that's where that 1.56 micrograms came into being. It then became embraced as a pass-fail, and that's the part of this equation that, of course, has it falling over. Now, what I can tell everybody is that in the automotive industry, as a specific requirement out of electric vehicle developments, which is more notably happening in Europe, but it's certainly gathering momentum under Biden's presidency in the US. So what we've got is companies demanding that if you're going to supply electronics to put into my car, I want you to meet this specification. Now, if you're delivering an engine management module, which was the case with Robert Bosch, then you can't test that using rows and give you a pass number that is lower than 1.56. And it doesn't mean anything. So what happened was that everybody started to rethink, why are we actually doing this test? And it is because we know that ionics cause corrosion. They cause breakdown within a certain set of parameters and conditions, humidity, electrification. To that extent, what is the technique that we can use that can give us a number? And the only technique that can give you a number is surface insulation resistance measurement, because it is measuring resistance. It's very specific. It doesn't tell you what's there causing a problem, but it does tell you you need to have a condition greater than 10 to the 8 ohms. If you don't, the risk of electrochemical failure increases exponentially. Now, this slide that you've shown up is taken directly from a presentation given by Robert Bosch some 2, 3, 4 years ago, and it shows examples of electrochemical breakdown, degradation, followed by electrochemical migration, a time to failure 500 hours. You've got metal degradation, dendrite growth between solder joints. You've got dendritic growth occurring across the body of a ceramic capacitor. You've got diffusion followed by electrochemical migration. So you can see that there are many different reasons for breakdown and for failure. And the problem for everybody has been to try to understand what the hell is SIR all about. So the first thing I want to try to communicate to everybody is that you have to get accustomed to the concept that it is for characterizing your material set. It is not suitable for qualification testing. And it's not suitable because in order to do SIR testing, we have to use a representative example of the intended end product, and we have to use dummy components. Why? Because if you have components that are real, the electrical performance is going to be radically different. And we're therefore now concerned with the assembly design, and for that purpose, you'd be better off to be using something such as DFR's Sherlock software that help the design engineer design to try and overcome the potential interferences amongst components and component legs, etc. So SIR per se is the perfect tool to give you a number. Ion chromatography, ROSE, FTIR can't give you a specific number without having a huge database of information relating to the loadings of various anions and within your test matrix. You will be familiar, mate, with the term of ion chromatography, and there we have to use a series of different columns. We heat the test solution to 80 degrees centigrade. We put the sample to be evaluated into that, and it gives us a spectrum. What it doesn't give you is a number as to what volume of each of those salts is critical to your longer term performance. So that salt loading is not an easy thing to calculate. Now, if I go back to the history lesson, where did the ROSE test originate? And it was very simply a simplified ion chromatograph. It was designed as a process control tool that would give you from an accept reject number applicable to every single product line, because it will vary from line to line, and that number you can dial in, and that becomes your individual pass fail. But will it tell you whether or not the product is going to behave long term in a reliable fashion, given the different environments into which circuit assemblies are placed? So we're looking here at characterization of a material set as opposed to a qualification. The objective evidence side of it, and people are asking, as you relayed to me earlier on, that where's the explanation of how to do this? Now, for reasons beyond my control, I can only tell you that I have issued to IPC. I was chair of the 532B SIR ECM task group, but through a series of debates, what we have decided to implement is a new residues assessment group. We've called it the Residue Assessment Task Group, and I immediately christened that the Rat Pack.
I don't know. I don't know if it's quite as cool as Frank Sinatra and Sammy Davis Jr. and Dean Martin, but when you put the word residue in there, it kind of lowers it a little bit, Graham.
Yeah, so
Got to come up with a cooler word for residues.
So what I've done is I've put together a document which is IPC TM650 method 2.6.3.7.1. And you can get that if you're on the committee, the 532G. You can get that document, and it is a test method using SIR for assemblies. Now, it complements very definitely the other IPC documents, which have been worked on extensively since Rev G was implemented back in October 2017. Rev H now integrates the white paper, which I commend anybody to read because it gives you a much more in-depth explanation as to how this all came about.
Yeah, I love the white paper. WP019, I think we're on Rev B like Bravo at the moment. What I find ironic about it is the amendment is 3 pages or 2 or 3 pages. That's what was changed in the standard. And the white paper is like 19 pages to explain the 2 or 3 pages of technical changes. But what I like, Doug Paul's was instrumental. I don't know if it was if that was a committee effort or if that was his solo work, but
no, I was part of that.
Oh, you okay? So it was a committee. What I like about what you guys did is you created scenarios. So they'll say, for example, company A has this scenario going on, and company B, and company C, and D, which I can guarantee in reading that white paper, someone is going to fall into one of those company examples and know exactly what to do. That was a great piece of work.
Well, Doug is really good at drawing those sorts of analogies. So they've also been embraced into the latest revisions of 9202 and 9203. So they are complementary to everything that I've spoken about so far. The two documents are just going to ballot right now, so I'm hopeful that they'll be being published by September, October of this year, hopefully sooner. But going back, if anybody is particularly concerned to have a standard that they can already work to, running in parallel with the work I was doing with IPC, I was doing the same with IEC. And for clarification, the International Electro-Technical Commission, with whom I'm very heavily involved, and ANSI, the American National Standards Institute, is the North American version of that. But there is a bit of a mismatch between IPC and ANSI because ANSI want more money than IPC want to pay. But international standards, we published 4 documents, and one of those happens to be the IEC 61189-5-502, and that is for assemblies. In a different variant of it, that's what I've published out as a draft to go to IPC. So the message in both sets of documents are exactly the same, but the wording and wordsmithing has to be somewhat different. One of the things that is not well understood is how we go about testing when you're running SIR evaluations. We're trying to measure resistance, and we're trying to do that using dummy components and looking at the interplay of each of the different process materials that the customer will use.
And Graham, just to set the stage for people who have no idea what we're talking about, surface insulation resistance testing measures the amount of electrical resistance between point A and point B, wherever those points are. The reason we use dummy boards or test boards with dummy components is because we don't necessarily on a production board have traces between the places where we would otherwise want to measure, right? So unless you build a test coupon on a breakaway part of your production board, you can't take a production board and subject it to SIR testing as we normally would on a sample board. So that's the reason why we have sample boards. You pointed out earlier, they're not the board you're going to ship to the customer, but they're supposed to represent the board with similar components and material sets, correct?
Well, let me try to explain the background to this.
Great.
The first time that objective evidence was ever done was 30 years ago. And the company that were using equipment that was the pre-production prototype of what is now AutoSir, our instrument, was GEC Meters in Stafford in the UK. And that was published in Circuit Technology in 1994. The work started in 1992, and indeed my area engineer, Jack McCaig, was actually the guy who did most of the prep work to actually run that test. Now, what the customer has to understand and needs to appreciate is that we're looking at the interplay between all of the process chemistries, and that starts with the circuit board all the way through to the final assembly. You've got at least 25 different individual chemistry steps in producing an electronic assembly, and nobody employs chemists anymore apart from the people who make the materials. In the days back in the 40s, 50s, virtually all the big defense contractors had a chemistry department, and they were examining exactly the interplays of all of this. It's the basic core of everything that we're doing today. And people are putting electronics in some really weird locations, in tough, hostile environments, and then wondering why they get all these sorts of failures.
Right.
You know, I keep getting questions almost on a daily basis from customers concerned very deeply as to, well, how do we go about this? And I say, well, if you don't know anything about chemistry, my best recommendation is use a test lab because they know what they're doing. So all of the work that we've been doing over the last 25 plus years has been with the test laboratories. I've worked with Trace Labs, NTS, SGS, and so many others, underwriters laboratories. All of them are using our equipment, and it seems to me the most practical route and pragmatic route for the guy who's producing, especially in small volumes, to use a test lab to actually conduct this experimental work for you to ascertain whether you've got a synergistically compatible material set that can give you the sorts of performance benefits to offset electrochemical reliability.
Let's take the test. Let's say I'm a manufacturer. I'm a OEM, and I'm making this board for a widget. And I just read the standard. I'm like, okay, well, so much for the old Rose numbers. Now I have to go do objective evidence. I have to do ionic testing, Rose testing for process control. But right now I need to set up my objective evidence. Standard says I need to run SIR tests and on similar components, identical material sets. So I call up Graham or somebody. I call up you, and I say, I want to buy one of your SIR testers. I don't know anything about anything to do with SIR, but I want to buy one of your SIR testers. And the standard says not only do you have to test electrical resistance, you got to do it in a harsh environment. You have to basically test it in an oven at temperature and humidity. And so I'm okay. So I buy an oven. Now I have your SIR tester, and now I own an oven. And I purchase some test boards, B52s or something, populate them, run them through my ovens, same profile as the production boards. Now what do I do? Now I have a tester, I have an oven. I'll say a layman, and when I say a layman, I'm talking about an electrical engineer or a manufacturing engineer that builds boards but doesn't necessarily understand SIR testing. So a layman from that standpoint, a newbie. Is it reasonable to assume that someone like me in that scenario could buy your machine or a similar machine, buy an oven and the test boards and understand the process easily enough to actually start conducting those tests in-house? You mentioned you recommend a laboratory. What's the threshold for bringing it in-house or sending it to a lab? That makes sense?
It makes complete sense. I understand it 100%. You have got to have a very highly qualified engineer who does have an understanding of this to a pretty high degree. Some years ago, Doug Pauls and I put together the IPC 9201 SIR Test Handbook. Read that on its own tells everybody loud and clear, I haven't got the time to do this. This is not something I can do quickly and easily. And more particularly, it's an expensive exercise because the equipment and the setup, as you've just alluded, is pretty high. To have the skilled personnel to actually run it, interpret the results, and give answers to the various questions, this is why a test lab would be far more beneficial to the user, because you'd be looking at something between, I would say, $4,000 to $6,000 to actually have them run the test using the B52 coupons. You'd have to produce the coupons, put them through your manufacturing process, of course, using the materials that you intend for your material set, of course. But what we're looking for in the test coupon is something that is a worst case example of residue entrapment. In your manufacturing and assembly process, you are going to have components that present challenges so that you've got different volumes of residue collecting around and underneath the components. Well, it's a question that I raised with the guys who make the cleaning materials as to when you have got components, especially bottom terminated components, especially like QFNs, you have got a very, very narrow area beneath the component, and the cleaning chemistry is engineered to be able to penetrate very, very tight spaces. Once it gets underneath those components, the residues that are trapped underneath, and of course we've got no control over how much there is, but the cleaning material starts to do its job, and it converts that residue into what I kind of helpfully call porridge. Now, if you've got that porridge
A highly
underneath,
technical term, yes.
absolutely, but it tells it. How do you can guarantee that you can get it back out from underneath the component? So trying to understand whether those residues are going to lead to electrochemical migration at a later stage, it's a hostile environment. We have a Venn diagram that we've been using for 25 years where we show that you need 3 ingredients to actually achieve a problem. And that is, you need an electrical current, you need to have humidity, and you need to have ionic salts. If you have one of those missing, you haven't got a problem. But the 3 things together compound to create a problem. So what we're trying to do using this technique is see how robust is your entire process to avoiding or mitigating against electrochemical failure in the longer term. Now, recently, a new paper was published by a gentleman by the name of Feng Li, who works for the Danish Technical University in Copenhagen. And he has just, for the first time ever, linked the wettability from a solderability test into how effective is that in looking at electrochemical migration using SIR techniques. And both he and Phil Kinner, now of McDermott Alpha Electrolube, their joint activities have shown that fluxes, especially no cleans, exhibit failures far longer in service than people would realize. I have been lobbying IPC J Standard 4, which is for the fluxes, to actually recognize this, because we need to examine and conduct the research to prove the point as to what is the qualification time frame for a flux manufacturer to say that his flux is good for you to use. And they only test their material. You're using several different materials simultaneously. So what we have already established is that we're looking to run 800 to 1,000 hours to try to determine what is the qualification point by which you can safely use those materials.
And the auto industry likes 1,000 hours. I've heard of many examples within automotive. No?
Sorry, Mike. I got to stop
correct
you.
me. Yes.
You are correct, but not in the context of SIR necessarily. What has been happening is that they use resistance measurement, which is what SIR is. It's
right.
Measuring resistance. Sometimes we're measuring on the surface, which is surface insulation resistance, and other times we're measuring actually within the laminate subsurface, and that's CAF.
CAF, yeah,
testing.
right, sure.
I can tell you that the initial kickoff, which was an ISO standard that was published in 2016, that standard said that you should do SIR testing for 1,000 hours, and they also said you should do it at different voltages depending upon your application. So if it's CAF, 1,000 hours.
And CAF, for those who are just tuning in to this issue, CAF is basically dendritic growth between the layers of the board. It has the three foundational components: electrical bias, conductive corrosive residue, and moisture. The only fourth thing that it requires, which is automatically available on the surface of the board, is a pathway. And so it exploits micro cracks or dry weave, breaks in the laminate to get between.
And not just that, if people are doing press fit connectors, you can expect all sorts of problems.
Sure.
Square peg in a round hole.
So basically subterranean ECM.
Exactly.
For those new to this conversation.
Now, what I can tell you is that approximately 5-6 years ago, the test conditions for doing CAF went up to 2,000 hours at 2,000 volts. And in September last year, it increased to 4,000 hours at 4,000 volts. Why? Because they found problems, and we're still carrying out the research. Now, one of the groups that you failed to mention my involvement with is our good friends at HD Pug, the High Density Packaging Users Group International.
That would have required a whole nother episode, Graham, to get into all those accolades. I
can bore for Britain. The situation is that HD Pug, we are leading a research effort to try to evaluate electrochemical performance at low voltage and high voltage, because there isn't any research work that's really being published at this stage. There's a lot that's being published on CAF, but not on SIR. And part and parcel of the problem with this is, where should you put equipment if you buy it? You didn't mention location of the chamber, the oven. You didn't mention where we put the equipment. Well, first and foremost, in measuring current, which is what we actually do, we're measuring down to picoamp levels. So the amount of interference that can be imposed from adjacent electrical equipment, especially high energy stuff, we've got customers who put an autosir in a chamber, and the room next door had a milling machine. Surprise, surprise, they couldn't get anything to read sensible numbers. It was all over the place because of electrical interference. So what we have to do is, when we're measuring at such unbelievably low currents, you've got to have this apparatus in a test laboratory. You can't put it on the shop floor. It's crazy to do that. Now, we have somebody in the United States that are telling people you can do this. I'd love everybody to buy our system because it's less expensive, it's easier to use, blah 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 blah. But I'd be doing them a massive disservice to tell them put it on the shop floor, because you're going to have horrendous problems trying to cope with this.
No, you're being impressively candid, because as a manufacturer, you're a manufacturer of a machine on the subject that we're talking about, and it would be very easy for you to say, yeah, just, everyone, you're required to run this test, everyone buy my machine, call now, operators are standing by. But then I assume part of it is, A, you're being authentic and honest, and B, you're going to get overwhelmed with service questions from A, all the lay people running it, and B, all the false readings you're going to be getting, right?
Mike, that's exactly the reason why I'm being as candid as possible. We've been doing this for nearly 30 years. I'm familiar with customers asking questions, and very awkward questions, very basic questions. We don't have the time to be able to do it. That was why I wrote the book with iConnect 007. It's why I wrote the webinar series along with my CTO, who is Dr. Chris Hunt. And for those who are not familiar, Chris was in charge of the Electronics Interconnect division of the National Physical Laboratory here in the UK. He left NPL in 2016 on the 31st of August, and on the 1st of September he was my CTO. I wasn't going to let
Didn't
him
waste
go.
any time there.
No.
And for our listeners and viewers of the show, I will have links to Graham's article, which is at iConnect, and all you have to do is fill out a very short form, and boom, there it is. No cost for that. And he also, through the same people, I believe, produced the video series, which it was highly produced, meaning very professional, and lots of relevant, informative, and attractive slides, so that you can get a deeper. If you like this subject, and you want to go deeper down the rabbit hole, that's the video series to watch. So I'll have links to both the articles and the book rather, and the video series. If you're watching this on YouTube, right down here it says "Show More." Click the "Show More" button. It'll give you a link. If you're listening to this on your favorite podcast app, Spotify or Apple Podcasts, wherever, click on the show notes and the links will be there. So back to you, Graham. Just a little bit of promo there.
Terrific. No, I appreciate it. I have to be candid with people because I've spent so many years working on standards. You can fool some of the people some of the time, but you can't fool all the people all the time. I want to be straight that if I was doing this and I was company D located in the middle of nowhere, and I'm doing maybe 100,000 assemblies a year, and they're being used in a hostile environment, what would be my recommendation? I'd talk to the test lab, get them to do this for you. Now, the follow-up to that, that's a different topic entirely, which I think and hope that I'll be coming back to talk to Mike again, but it'll be after episode 100, and that is to talk more about PICT, which is the update to ROSE, because that is by far and away the optimum process control tool, inexpensive, quick, accurate, sensitive, that you could possibly do. And we've supplied that with Six Sigma verification with Robert Bosch all over the world, and with a huge number of other customers, because it is quick, easy, and it's not expensive.
Right, and for our viewers and listeners, IPC requires for this cleanliness assessment, cleanliness quantification, an objective evidence be formed using SIR under heat and humidity conditions, as we've been talking about for the greater part of the last hour. And then it requires ionic conformation, ionic extraction type testing, commonly referred to as ROSE testing, and the variations of that, PICT, things like that. It requires that for process monitoring. So whether it's ROSE or PICT or extraction, localized extraction, whatever the put it in a baggie, the old shake and bake method, early ROSE test methods. That's what we're talking about for process monitoring. That's a requirement as the standard.
Sure, but what you would do is to take the coupons that you have actually done the SIR test work on,
right?
Put those then, after the testing, into your ROSE tester, whichever model you may have, and average out the readings that you obtain.
Right.
And then you can set your own pass-fail limit. And we've got customers who have got a pass-fail for their own production line of 0.02, and I've got others that are at 3.
Right.
So
that's the beauty of the new standard. It is relevant and relative to the customer's product. If a customer has a board that passes SIR, and then they subject the board to ionic testing, and they have a 0.2 or a 22.2, doesn't matter. Because
Exactly.
you've proven that a 22.2 or a 0.2 or anything in between correlates to an SIR result that's a pass. And we assume
Exactly.
if it doesn't fail within the prescribed SIR test time, that the product has a chance at not failing also. I want to go back to your point very, very quickly. We have to start tying up all our loose ends. You talked about no clean flux and the Feng Li's talk about that and how longer duration tests should be required. I think one of the things I've been railing on for years is if we want to change the mindset, we need to change the term no clean to low residue, because no clean, the most common flux removed today, Graham, by far, no clean. More, and that's not because no cleans all require cleaning. It's because almost everyone is using no clean, and then they decide, through all these different reasons, now we have to clean some of those boards. Well, we're not going to change back to RMA or water soluble. We're just going to keep using no clean and clean what needs to be cleaned. Particularly common in a contract manufacturing environment. But no cleans are regularly cleaned, and more no cleans are regularly cleaned because they just don't survive the SIR testing. But if we were to just change the mindset to, if you're not going to clean, then you have to run a very low residue flux. But if we just change the name to low residue, it sets the mindset that there's stuff on there, and it may be harmless, it may be harmful, but there is stuff on there. And then the fact that when you don't remove the flux, nothing gets removed. Everything, all the sins of the process, from fab to board fab, component fab, dirty humans, they all come along for the free ride, right? So that's a big issue. Should we be, if someone is running, there's two reasons someone complies with the IPC standard. One is to check it off the list, just a check item, check mark. Okay, we did it. It says 168 hours. We're not going to run 168 and a half hours. We're going to stop at 168 hours and pray it doesn't fail. And then there's people who are embracing the standard because they truly want to make sure their products are not going to fail. They're using it as a tool, not just a checkbox. For those in the latter group that are testing because they really want to know if their product is safe to ship from a reliability standpoint, should we be happy with 168 hours? Some of Feng's work, Feng Li's research insinuates a longer test time. Part of Phil's talk about more.
What he's done is to examine the interplay of the different chemistries that are used in no clean fluxes. And the problem is far greater than people realize. How critical is that to your end product? Is somebody going to die if your product fails? Then don't take shortcuts. If somebody might get inconvenience because your phone failed, who cares? And really, that's what it boils down to. When we're dealing now with electric cars, and this has been a massive subject for me over the last 7-8 years, the amount of testing that has to be done and still needs to be done is truly scary. I can't begin to explain it all. And we've got one test laboratory alone, albeit in China, who've got over 50 systems that are still running 24/7. It's, if you're going to see a failure, you want to know when I'm likely to see it, and can I do anything to mitigate against that? And the auditor is the guy who's going to tell you whether or not you are going to pass or fail the requirement. So I can only say you need to have an engineer suitably qualified who really does understand this subject if you're going to do it yourselves. We've got lots and lots of customers, hundreds and hundreds of customers all over the world. and certainly the larger proportion of test laboratories, and they've all got multiple systems for this very reason.
Well, one
So,
of the challenges, I think, logistically with SIR testing is because the test time is so long. I mean, at minimum, it's 7 full days, right? 7 24-hour days, 168 hours. In many cases, it's more than that. Once you close the door on that oven and you start recording on the tester, if someone comes up and says, I want this board tested, you either have to have another tester available or you have to wait a week, right? So,
well, not unless what's in the chamber's failed, in which case you can
well,
switch it
true.
on.
If you fail in 8 hours, then
Yeah.
next. But I guess that's another reason why test labs might be a better solution than trying to do it in-house. In addition to the reasons you've already mentioned, there is that logistical, it's an elevator, basically. Door closes and it doesn't come back until it's empty, so to speak. So that might be a long wait in the lobby for the next elevator. And if you're an OEM, are you going to buy 8 machines just so that you can keep, new products flowing through it? That's a logistical concern. Of course, from your standpoint, you'll just make more. Right? You just make more machines, no problem, right?
Well, I have to be honest with you and say that sales over the last 5 years have gone up meteorically. I mean,
Sure.
It's been phenomenal. And my younger son has actually stepped up to the plate thanks to COVID, and he's taken over the day-to-day running of the business. So as this video shows, I'm actually working from his old bedroom at home, where I can just focus quietly on the job in hand in terms of helping customers understand the situation, understand the scenario, deal with the standards, try to give the advice and support without having all the day-to-day stuff that he has to now take care of.
Right.
It's great.
Yeah, I'm in a similar part of my life with my business as well. And I get to do things that are fun. You and I both built businesses where we did things that we had to do, whether we were good at it or not, because there was no one else around to do it.
Exactly.
And it is nice when you get to the point where you can put talented people in to do things that you once did because you had to, and they do it because they're really good at it. In many ways, like I'm sure this is, well, I don't want to assume for your company, but certainly for my company, many parts of the company are running way better with me not there than
I know.
with me there.
It's quite a worry.
Yeah. I mean, it's hard to admit, right? And
Yeah.
fortunately, I'm admitting this to all these people, but it's true. Our talent, your talent, you're supposed to be the visionary. You're supposed to be the guy in the crow's nest. You're supposed to be the guy with the mad scientist with the crazy ideas, and other people figure out how to get your vision accomplished, right? That's the way it's supposed to work. But many founders stay on the factory floor for way too long, and then they just run their company into the ground, right? That's just what happens.
Exactly.
So welcome to the club. It did take some getting used to, but it's great from this vantage point. Before we wrap up, it took, because we could talk about this all day, it took about 50 years for our industry to change the way we viewed cleanliness as it related to reliability. Do you think it's going to take another 50 years? It sounds like there's already work in progress to make modifications to this new strategy. But what direction do you think we're going? What timing before things change? Will it be a radical change? Will it just be fine tweaking to the current methodologies?
I think it'll be fine tweaking of the different methodologies. All of the work has been done, and it's been done over a 30-year time frame. This is not brand new. It's just that people have avoided doing it because this seemed too complicated. Put it on the too hard tray. Leave it alone. Well, you can't do it anymore because a lot of companies were telling their supply chain, you've got to do this according to that standard, and that number is golden, the 1.56. Well, it isn't. It never was. And now we've proved it.
Let me ask you as a final question, your advice to people embracing the standard, particularly for the first time, is to contact a lab, particularly if they don't have the right environment or the knowledge, which no one should. Why should they? Other than a lab, what would your advice be in seeking out a lab? What questions should a potential customer ask? I've heard of people going, yeah, we can do SIR, but they're not really necessarily in our industry. So are there certain vetting type questions that one should ask?
Well, you certainly want to have a formally accredited lab. You need to have people who know exactly what you are looking for when you use the words, I have to do an SIR test, I have to evaluate. I've given you some names of labs with whom we have a very close working relationship. We've worked with Trace Labs for over 25 years, NTS, SGS, Precision Analytical Laboratories, Underwriters Laboratories. They're all over the US.
Sure.
So I can't, from where I sit here in lovely old England, I can't tell you exactly the nearest lab to you, but you probably your first point of call would be to have a look at IPC's test lab directory, and I suggest SMTA have probably got a good listing.
Yep, sure.
Yeah,
and if they're tied to IPC or SMTA, then obviously they got a stronghold in our industry, so they'll understand the nuances and the standards that you're trying to meet. And exactly. Then, so if someone fails an SIR test, that's, I think, when working with a lab, I'll use Foresight as an example.
Yep.
They'll do SIR testing for people, but they also have on chromatography. They also have a lot of experience, as do other labs, in interpreting. So you can find out you failed. Okay, that's disappointing. Our product failed. Why? They can tell you what was on it. They could tell you from a chemical analytic standpoint that this was, this is a flux residue, or this is a mold release agent, or this is a cleaning solution not rinsed properly. They could show you where the usual suspects were on the board.
My own personal recommendation is that you should be talking to your supply chain in terms of solder paste, flux, wire, etc., and find out what their SIR data is for their material, and have they got a list of customers, suppliers that have supplied lots of material and they've already done all of this work, because that will narrow down the problem area.
Well, excellent advice, Graham Naisbitt. Thank you from Gen 3. Thank you for agreeing to be my guest. It's always a pleasure to talk to you. Anytime I talk to you, I feel like I know less. Not because you don't explain it well, but because I realize there's a lot I don't know. So you're always a huge vault of information, and one question generates 10 more. That's what I mean by I feel I know less. I appreciate your insight. I appreciate all the work you do in our industry. We are colleagues. We are competitors in one small part. But you are quite professional, and you run a good company. You build good products, and your company performs a very valuable service, particularly these days. You're getting old when you start using terms like these days, right? But here we are, these days. But these days with IoT, you talked about earlier, electronics are going into very strange places and strange applications. That's the role of IoT, to put electronics in things that never had them before and probably don't need them. But there we go. And then, things that were electronic, like in cars, that were infotainment systems and seat massagers or whatever, stuff that could fail and nobody would die, now are really controlling whether we live or die. They're engine management systems, ADAS systems. It's like, this stuff can't fail. And
exactly.
So it was good timing for IPC, probably a little late, but at least it got the attention of the world, and they changed the standard, and that was well timed and needed. And I think it's just going to get even more critical. We build boards at the edge of the envelope today, way closer to the edge of the envelope than I think we ever had. And normally, new technology would come out, we're at the edge of the envelope, and then all of a sudden it becomes mainstream, and we're now in the middle of the envelope, and something new, BGAs drop on us, and we're at the edge of the envelope, and it's the world's worst part, and then it's no big deal. Now, QFNs are the world's worst part, and pretty soon they won't be any big deal. But I think we're just going to be kind of forever, permanently at the edge of the envelope. I think that technology is coming up faster than we can process how to use it. And the way our industry works is component designers drop components on us, which are brilliant components, but they don't tell us how to place them. They don't tell us how to clean them. They don't tell us how to test them or inspect them. We have to figure that out as a group.
So true. Mike, I can only say thank you very much indeed for giving me the opportunity to talk. I'll be happy to converse with any of the listeners at any time. You'll have my email address.
Yep, that'll be in the show notes. So we'll have links to your video presentation, your book, and your email address. We'll keep your address private, so people don't go knocking on your door asking you to run some tests. So we'll respect that. But Graham, a vault of information. Thank you so much for being my guest. Thanks for all you do for the industry, and particularly with the standards and the various agencies you work for. I appreciate that. And we'll talk again soon. I look forward to actually seeing you in person.
Yeah, I'll look forward to getting back over to the other side of the pond. Hopefully the back end of the year, definitely the beginning of next.
Well, Apex is coming up in January, I think. So we might see you then. Yeah, in San Diego. Worst places to be in January. All right. Well, thanks a lot, Graham. I appreciate you being here.
Thank you, Mike.
Well, that's another episode. Thanks for listening to or watching the Reliability Matters podcast. Don't miss an episode. Subscribe to Reliability Matters on Apple Podcasts, Google Podcasts, Spotify, and on our newest channel, Amazon Music, or virtually anywhere you get your podcasts. A special thanks to Circuit Assembly Magazine's PCB Chat at pcbchat.com and Ascendo Reliability at reliability.fm for syndicating this show. And be sure to watch our 100th episode live special, July 26 at 10 a.m. Pacific, on LinkedIn and on YouTube. Follow me on LinkedIn to watch the special live episode on LinkedIn, or subscribe to the Reliability Matters podcast on the Reliability Matters YouTube channel. Thanks for your questions and episode suggestions. Please keep them coming. Send episode suggestions right down here to Mike at mikeconrad.com. That's Conrad with a K. Once again, thanks for listening. Stay safe, stay healthy, stay happy, and perhaps most importantly, keep doing it right. I'll see you soon.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.